Hello guys, and welcome to my wind tunnel plane experiment. So this is my science fair experiment. First, I'm going to tell you some background information. So we're going to learn about some planes and wind tunnels. So first of all, let me just tell you a quote. Man must rise above the earth, to the top of the atmosphere and beyond, for only thus he will fully understand in the world which lives. Now, this is a very famous quote by Socrates. Now, he is saying that humanity one day must go beyond the ground. One day they must fly like birds. And only then they will fully understand their world. Right now, we do have those machines that can fly, but there are still big problems with them, like not being efficient enough, or sometimes like crashing. And today we'll be trying to solve some of these problems. To solve these problems, we need something called a wind tunnel. So the wind tunnel sounds just like what it is. It's just a tunnel with wind going inside. So it is used to test something that simulates like it's in motion. So there is kind of like an aerofoil or a plane, a rocket, or maybe like a race car, because race cars, they want it to be as aerodynamic as it can be. So it simulates something in motion. So it is way better than just making a plane go into the air. Because what if it doesn't work? Like, if it doesn't work, the plane will crash to the ground. But in a wind tunnel, there won't be very big problems if the plane did not work. So just imagine you tested 100 times, and all these 100 times did not work. If you were not using a wind tunnel, you would have 100 broken planes. But if you used a wind tunnel, you would probably only have 0 broken planes, or a couple. Not a lot compared to 100. So it just kind of just simulates it's moving. So when the wind is blowing back, it feels like the object is moving. Like when you're running, wind blows back. But if the wind is blowing back and you're just running on the spot, it feels like you're running, but you aren't. So it can test the aerodynamics, the lift, or the control of the planes, because aerodynamics is very important, and lift can be tested in an aerofoil plane, and a rocket or a car can be tested if it's in motion. What will happen? Will it go out of control or not? So the object in a wind tunnel is actually normally scaled down. Let's just imagine a 60-foot plane. You wouldn't want to make maybe a 100-foot wide wind tunnel. That would just be a waste of material. You can just make a small version and it would still work. But we need to make sure that the version is exact, like the same wing shape, same type of fuselage. All of the stuff has to be constant. Okay, here are the 3 wing types that I used in my experiment. So the first one is the Ogive Wing. Now, the Ogive Wing is a wing that is roughly kind of triangular shape. There are some curves sometimes in there, but they're only just to increase aerodynamics. But this time, I just used a perfect right triangle. So it's mostly used in supersonic, just Mach 1 to Mach 5. So 1 to 5 times the speed of sound, which is quite fast. But hypersonic is even faster, like Mach 6 or beyond. So an example of a supersonic plane that uses Ogive Wing is just the Concorde. And a hypersonic one may be just like SR-72. Now, I'm sure that you do not know a lot about SR-72 because it's still being kept secret, but we know that it is going to have an Ogive Wing. So an example is a Concorde. Next is swept wings. Now, swept wings are very common. If you've been on a trip or on a plane, I'm sure that you've always met swept wings, like the slow flying aircraft. I'm meaning like from less than the speed of sound. They all mostly have swept wings. So basically, the passenger liners or some like C5 Galaxy. Those are only some of the examples of swept wing aircraft. So they are used in subsonic and sonic, just less than Mach 1 aircraft. Okay, so last but not least, cylindrical wing. So cylindrical wings are very, very rare. I only know one type of plane which has cylindrical wing. It is a French tail-sitting aircraft called the Coleoptère, and it was made by a very good, very looking forward visionary. Now, just telling you, this aircraft failed not because of its wing, it was because of its tail-sitting way. So there can be possibilities that one day there will be cylindrical wing aircraft going into our skies. So there are some advantages about this. It does not need tailset, first of all, and it does not need winglets. Winglets are a big problem in all of like the whole aircraft industry. But not needing winglets is just mind-blowing because winglets are just like the biggest problem you can ever have with a plane. Okay, next is a scientific method. So I'm right now going to explain scientific method from the start, purpose to end conclusion. And this is all going to be based on my experiment. So here is the purpose. So find out that do the wing shape change the aerodynamics of the plane? So here's my hypothesis. So I would think the tube-shaped wing, or if you would like to call it the cylindrical wing, does the best. So why? Now, less surface area exposed outward, so more aerodynamics. And no winglets, which is a very good improvement. And we can also add ramjet propulsion. So ramjet propulsion works like this. So there is like this tube, and there's kind of like this kind of little bit of a cone in front, which compresses the air because it only works when it's already moving forward. So air comes in and then it's compressed, and then it combusts with fuel, then it's jet backwards, which is very efficient. But a scramjet is even more efficient. But let's not really get that much into this. Just saying that it can have one type of engine like a turbojet, then have a ramjet using its wings. So it can create a lot more propulsion. So that is only some of the reasons why I think this cylindrical wing is the best type of aircraft. And right here is a drawing of the Coleoptère. So here are the materials. Here we'll start with cardboard, which I already had in mind before. Now, just before I go on, I had 3 main big designs and 2 of them failed. So I also had one design at the start, which did not use a lot of materials, but at the end I used quite a lot. So I started with cardboard, to make kind of like we use cardboard to make the planes and hot glue to glue the hot cardboard together. And we also use plexiglass, which we used to make kind of like a transparent wind tunnel so we could view into it. And 2 ventilation system openings, which kind of made like the frame of it. So you can see them here, like the metal stuff. And then we have like small nails, which we nailed the plexiglass on. Then we have duct tape, which it was a very big the improvement to our project. Without the duct tape, nothing would have worked. And next we have 2 long nails. Can't really see them right now. You can only see this tiny little point right here, which is the tip of the nail. There's also a vertical one here. Next we have the scale, which you can't see right here. The scale is used to test how much mass there is. And we'll be transitioning the mass into force later. So next we have the string, which we connected the plane to the weight, and we would be measuring the weight on the scale. And the needles, which we attached the string to the needles, we use needles because needles are thin, they're small, so they won't really affect the aerodynamics. But let me just tell you, this is a very, very, very bad test for good science compared to it. Next, we have popsicle sticks, which you can see here. We used it to make the tracks. And then we had adhesive. Adhesive we used to glue up the cracks, like right here, to not let a lot of air escape. So that was a big improvement of our project, and it made it a lot more reliable. Next, we had the weight, which I said before, we attached it to the string. Then the pitot tube. The pitot tube, if we did not have it, it wouldn't really affect our project that much, but it tests how fast the airflow is going. And we tested it's about 28 kilometers per hour, which is quite fast. It's faster than the fastest person on Earth, which runs 27 kilometers per hour. So next, we had the vacuum, which played a big role in our experiment because it was the one that was blowing air. Now, we actually flipped the vacuum around, so it was not sucking, it was blowing. So here is the procedure. So I will not be going over this really thoroughly, but as you can see before on the last picture, that was basically the simple experiment setup. There was the plane inside with popsicle sticks, which I fixed it on. Then there were 2 ventilation systems, and then I nailed 3 pieces of plexiglass on the sides and put the top one for the lid, which I taped on with one piece of tape. And then I cut the string into a long, long strand, which I stabbed 2 needles inside on the 2 on string. The other end was put onto the weight. And then I put the long nail vertically on the front and nail it horizontally. I fixed a rubber band to the vertical nail. Now people will be thinking, why are you going to do the rubber band? Now, let me just show you here. I've got string right here. String can only stretch so far, but a rubber band, as you know, can also be called elastics. So it shows that it's very elastic, and it can be just like how tight a rope is, but it can be like a lot tighter. You can just pull it very, very far. So we found out that was a big flaw because ours at first did not really work. So it was just going like this, and then it was not changing. So our first test way was a fail. So we had to use rubber bands. We fixed the other end to the head of the needle because we had like needles with the large bulb at the end. And then we fixed the other end to the rope on the weight. So the weight we had to put on the scale, and we tested like the more it was on the weight, the less aerodynamic it was. So then we fixed the popsicle stick to plane vertically, added tracks out of popsicle sticks. We made it out of popsicle sticks. And then we fixed the pulley to the back, and we put the rope for the pulley. Like the pulley was basically just the long nail. So we started the motor, and then we started collecting data. So here are the observations for my first experiment. So my observation is this plane did shake, which was a good sign. It showed that the wind was moving. The less the weight on the scale, the less aerodynamic it was. Now that design did not work because there were multiple reasons, like the vacuum wasn't strong enough. That was like the biggest reason. We found out that the vacuum could not create kind of like a jet of air that would push the plane backwards. So we had to flip the vacuum around to change it from sucking to blowing. So that was a big improvement, but it still did not work because the scale went like kind of crazy at times, where it was like going all around there. It went like data went high down, like went all crazy. So I could not really get my data. So here's the successful way. So this procedure was made for this one. So I added tracks to it and flipped the vacuum around. So last time it was blowing here. Now it's blowing right here. So the larger the weight, the less aerodynamic it is. The plane did not shake, which right now is a good sign because without the plane shaking, we would know that there is no other interference with it. Okay, here's the data of my experiment. So I got the difference from the airflow on, airflow off. Then I got their difference, and then here is it, the drag. So this is actually in grams. So after, I'm going to convert it into a force. So here are the data of my cylindrical wing. The last one was the Ogive Wing. Right now, here is the swept wing. So you can see here from all these data, which one do you think would do the best? So if you look closely, you would actually think the cylindrical wing. Okay, but I'm going to reveal this answer in the next slide. So here are some math equations. So here's delta M, which I've got the difference of the masses. So remember, my first trial of the Ogive Wing was free. So that is my first delta M. Then I add the other delta M for like trial 2, and then trial 3, trial 4, trial 5. Then I divide it by 5. And then it equals the mass. And then I used Newton's second law, which is F equals ma, a very famous equation. But now, remember, A is 9.84 kilograms. So we are going to divide it by 1,000 for grams because ours were 4 grams. So then we will get 0.0098. Then we times it, and then we get this. So here is a graph of my data. So for the first trial, the swept wing did the best. And for trial 2, the cylindrical wing was the winner. And for trial 3, the cylindrical wing won again. And for trial 4, the cylindrical wing and swept wing drawed. And then finally, trial 5, cylindrical wing and the ogive wing were tied again. Okay, so that's just all the data added together. Now let's average it up, and then let's get a drum roll to see who is the best. Okay, so as you can see here, the cylindrical wing did the best. So here are the averages. So the drag is now in newtons. So here's ogive wing, cylindrical wing, swept wing. Cylindrical wing, as you can see here, was a lot better than all of them. And ogive wing, I don't know why, but it did the worst. So conclusion, discussion. So my hypothesis was proven correct, which is very happy. I'm very happy. And people say that elliptical wing is the best type of wing. So I did not really test the elliptical wing in this project. So next time, if I'm going to do this project for a science fair, I will be trying to test an elliptical wing. So my test shows that cylindrical wing is the best. And this type of wing can lower the fuel of a normal plane. Like imagine it used 100 kilograms of fuel for a flight. Then it may be kind of like 90 kilograms of fuel for a flight, which if you do all the planes in the world, you'll get a huge amount of fuel that we don't need. And that is not only good for us, but good for the world, because you know that right now the jet engines, they're not considered that good. Now I mean good by helping the environment. So they're making global warming a lot more worse. But using less jet fuel, that can lower global warming a lot. And it can also make plane tickets less costly because you don't need that much fuel. So it can be like an $800 ticket to lower to a $750 ticket. Now, that may not seem like a lot, $50. But let's just say one family went on 100 trips. Each, they saved $50. Then we do the math and we get $5,000, which right now we can think is quite a lot. $5,000. You can buy a lot of stuff with that. Okay, so here is the conclusion. So my test results support the hypothesis. Now it may seem like the whole thing is finished. My test was correct. But let me just tell you, the test was not really that fair. Like, free flaws can be like, the vacuum was not straight, the string was not straight, the plane was not perfectly horizontal. So these are only some of the big flaws we had in this experiment. This experiment would be considered like one of the worst experiments you can ever do if you would want to do good science. So next time, for future directions, we should always have a controlled airstream, because sometimes we should be kind of make the airstream not really that constant. Sometimes it's blown this way, sometimes it's blown that way. Now I'm just exaggerating, but it is not straight. And we can also have almost everything constant. We also did not make the plane's wing area the same. So next time, that is one of the things that I need to focus on. So we next time is just need to keep everything constant. try my best to keep everything constant because we need to keep the things that we want to do constant. And we should change the independent variable and get the dependent variable. Those should change, but constants like the wing area, the airspeed, the direction, those are constant. They should not change. So here are some additional links. Here is like in Wikipedia, the Wikipedia page about wing configuration, a type of aircraft wing link. And here is a YouTube video about coleopter, cylindrical wings. And here is an interesting engineering.com one with 9 of the most common wing designs. Okay, so thanks for you guys coming to my presentation today. And hope you have a great day and happy science.